All right, we have 9.3 next. I do want to go back real quick to the end of 9.2 and just reiterate that I would rather you focus on this part of the test. So test number 1 is the nth term test for divergence. And basically it says if the limit's not 0, it's divergent. That's all it tells you. It doesn't say anything about if the limit is 0. So ignore that, okay? If the limit is not 0, it's divergent. 9.2 has 2 tests involved, the integral test and the p-series test. The integral test brings us from a series into what we looked at the end of chapter 8, which is an improper integral that would have to be rewritten, use L'Hopital's rule, all of that stuff. So you're going to see a lot of chapter 8 fused into chapter 9. It says in this section you will study several convergence tests that apply to the series with positive terms. So the integral test is as such. First of all, it only works if the function, okay, is positive, continuous, and decreasing. So what we do is we take this sequence and we treat it as if it's a function. Okay? Take the sequence and put it in its function's place in the integrand. We trade the n equals 1 to a lower bound of 1 and the infinity to an upper bound of infinity. If the integral converges to a number, then the series converges to a number. If the integral becomes infinity or negative infinity, then the series becomes infinity or negative infinity. So either they both converge or they both diverge. Notice that neither the last test nor this test tell us what the sum is, just whether or not it is convergent. Or whether or not it is divergent, rather, with the last one. So, integral test. We are going to trade the series notation for the integral from 1 to infinity of x over e to the x squared dx. And we're going to solve that integral. It's an improper integral that needs to trade the upper bound with the letter b, and we'll let b approach infinity. And I'm going to actually rewrite this as e to the negative x squared. Well, this is going to be a traditional u sub, where u is equal to negative x squared and du is negative 2x dx, which means I will have a negative 1/2 out front, and then I'll have negative 2x rather, dx on the inside. So I plugged in here and balanced it here. I'm not going to actually write the u's and the du's. I'm just going to know that it's already e to the u du, and I'm going to integrate that as e to the u plus c, except it's not plus c because it was a definite integral. I have the limit as b approaches infinity of negative 1/2 e to the negative b squared minus negative 1/2 e to the negative 1 squared. Okay. I'm going to simplify how this looks, make it look a little bit cleaner. My first term, that e is going to bounce to the denominator because of that negative power, so it's negative 1 over 2e to the b squared. These two negatives become a positive, and it's going to be e to the negative 1, which is going to be 1 over 2e. If b is ever increasing, then this is going to approach 0, which means my final answer is 1 over 2e. It's an ugly number, but it is a number. Because that is a finite number, then the series converges. As long as this isn't positive or negative infinity, The answer is that it converges. So that's an easy test. The third test we talk about is the test for p-series. P-series are identified as a specific exponent attached to your denominator. So, for example, you see down here 1 over n to the 2/3. If your p, which is the exponent, is greater than 1, then your series converges. But if it's between 0 and 1, including 1, then it diverges. This is different than your geometric formula. Remember, geometric, if it was between here, it was convergent, and if it was greater, it was divergent. So make sure that you understand your rules. So here's what I know. This p series, it's 1 over n to the p. So this exponent is your p value. P is 2/3. Which category does 2/3 fall into? Hopefully you recognize it as this one. Since it's less than or equal to 1, then I know that this is divergent. That's all I know. Okay? Done. That's as simple as these questions. Identifying and then boom, done. So this series isn't written in summation formation yet. So we're going to put it in the sigma notation and then analyze its value. This could be written as 1 over 1. And if you notice, the denominator is increasing by n, starting with an n value of 1 and going toward, whoops, I didn't need that part, going toward infinity. Okay, so this is a p-series with a p-value of 1, right? The exponent on all of these is 1. 1 happens to be in this interval. Sorry, wow, brain fart. Therefore, this sequence, or this series rather, is divergent. Now, if you saw the same sequence, but it was the 1/2, 1/9, 1/16, 1/25, you know that your p-value was squared. That number is greater than 1, so that would be a convergent sequence. This series. This series up here is called the harmonic series, and there's reasons behind it. This is another one of those things like Fibonacci's sequence that is worth looking into further. There's a statement on page 607 that says this: Pythagoras and his students paid close attention to the development of music as an abstract science. This led to the discovery of the relationship between the tone and the length of the vibrating string. If you've taken physics, then you already know that there's a connection between how the string is vibrating, what it looks like, it's a sinusoidal curve, like a sine curve, and the tone, or the note that it's playing. It was observed that the most beautiful musical harmonies corresponded to the simplest ratio of whole numbers. Later, mathematicians developed this idea into the harmonic series, where the terms in the harmonic series correspond to the nodes on a vibrating string that produce multiples of the fundamental frequency. For example, 1/2 would mean that it was 1/2 is twice the fundamental frequency, 1/3 is 3 times the fundamental frequency, which is how often it shows up, and so on. So a quick visual. If this is the curve of one whole unit, if you will, then if I take half of that and look at these are all terms of the harmonic series, or the p series, where p is 1. If I break it down into half, then musicians have decided that this sound from 1 to 1/2 would make a good sound. 1/3, 1/4, 1/5, 1/6, 1/7. These created the notes in a traditional scale, and that's why they're using the word harmony, because it sounded good. Okay? So look at that further. I'm certainly not an expert on it, but it's worth looking into at a deeper level, especially if you're a musician.